Hi, folks. I'm Anna, a PhD student at MIT, and I'm excited to present this vision and new line of work we call causal data integration. This is joint work with Britt Youngman, Mike Caparella, and Babak Salimi. Causal inference lies at the heart of empirical research. However, when conducting causal inference, we find that data management problems can lead to false discoveries and consequentially impact scientific progress. Answering such causal questions is critical for decision-making in business, education, public health, and beyond. We're seeing growing interest and impact in the causality space here at VLDB and SIGMOD. These are all just the papers from last year. With this work, we want to add to this great research momentum and energy. In addition, many of these query explanation hypothetical reasoning papers make input data assumptions that can be met by using this vision paper's new line of work. Of course, if you join us working in this area, you're going to be in great company. So to help our community help causal inference and boost scientific progress, we identified 3 research opportunities we as a research community can contribute to in support of a larger goal. And that larger goal is causal data integration. So for the rest of this talk, we're going to walk through a quick review on causality, dive into these 3 research opportunities, sketch out a high-level system architecture, and round it out with a prototype case study at the end. For science. All right, first, let's walk through an example of causal inference in action using the Pearl causal framework. Let's say we want to know, how much does picking any particular airline carrier affect flight departure delay? The first thing we need is a table of observations. Here, we have a hypothetical slice of a flight delays dataset. Crucially, this table has 2 important columns, the treatment and the outcome. When we ask a causal question, we ask, if we change the treatment, how would the outcome change? Here, our treatment is the airline, and the outcome is departure delay. So of course, to answer this causal question, we'd want a table of observations which describe when the treatment and the outcome take on different values. But let's take a moment. Why do we need causal inference? What if we just group by airlines and we looked at the difference in average delays? Well, that might lead to a spurious correlation because some airlines fly out of congested places more, so that's out. Or what if we threw machine learning at it? We could predict the delay based on the data we have and we can compare. Well, statistical and conventional machine learning approaches are fundamentally associative. They employ correlations rather than causations to make their predictions. So let's say we use some associational method to make predictions using highly correlated features. This is actually lead you to a logical fallacy called affirming the cause quit. After all, if your plane takes off late, that delay is going to contribute to your plane landing late. You're using a consequence of departure delay to predict departure delay. Perhaps with strong feature selection methods, conventional machine learning methods might not fall prey to this conundrum, but if you have a causal graph, you can avoid such problems simply through static analysis. So returning to our example, we know the second input we need is a causal graph, which describes how each variable causes another in the system. So from the table that we have, each column becomes one node in the graph. And we allocate edges to the graph according to background knowledge, which is what we know about the world already. So we know airlines contribute to departure delay, delayed takeoff leads to delayed arrival, and so on and so forth until we finish populating the graph. And based on the structure of this graph, we know that these nodes, the other ones, are important to adjust for when answering our causal question. Now that we've completed our overview of causality, we know that in an ideal world, answering causal questions requires 2 inputs, a single pristine data table and a perfect call tag. But in the real world, we don't have perfect data. We don't even have a causal graph. We just have real-world databases. This data preparation gap is actually pretty high. The required inputs for causal inference are almost always marshaled assets by people who took the time and effort and care to curate data by hand, often from integrating multiple external data sources. So the goal of causal data integration is to significantly reduce the effort required for practical causal inference. To do that, we envision building systems that automatically mine the missing data and background knowledge necessary for answering causal questions. So to better understand these challenges of constructing causal inference-ready data sets, let's look at 3 problems that can bubble up when our input data is unreliable. So the first issue is that tables with missing variables can introduce latent confounding bias. This bias easily arises when attributes we need to adjust for aren't in the table. So let's take a look at a scenario where we're missing information about weather. So based on the first 7 columns of this table, we might conclude that American Airlines is just not effective at departing on time. But if we had a data lake, perhaps we could use some data discovery. It'll just find the relevant columns that will be useful out of that data lake, right? These methods can successfully find attributes that are correlated with the treatment or outcome. In this case, we're able to recognize that traveling during winter break is correlated with flight delays. Sure. What's great is that in a predictive scenario, having this information can result in more accurate departure delay predictions. However, these attributes aren't useful to adjust for in answering our specific causal question. In fact, using some correlated attributes as potential confounders could result in exacerbating biases which we wanted to control for. In this case, we run into the same admitting the consequent issue because employee sentiment could be determined after the flight has departed. Alternatively, instead of having a data lake, let's say we have a big pile of videos from the live feed from each airport. What if we could mine attributes from them? We'd be able to recognize that with the missing weather condition column, we see that American airline flights on the table had heavy snow and thunderstorms impacting the flight departure. Any airline dealing with heavy snow and thunderstorms would also run into these flight delays. So American Airlines operating these flights doesn't entirely explain the departure delay. So adapting methods that find joinable tables in a data lake and build relations out of knowledge graphs are actually crucial for this step. We could imagine to adapt these for a causal domain, we could extend existing, say, data discovery algorithms like STARMY to use relevance criteria specific for identifying potential confounders. Perhaps we could use semantic information in conjunction with correlational relationships as clues to potential confounders. And for knowledge graphs, perhaps we can modify systems that build relations from knowledge graphs to traverse multiple edges in order to reach causally related attributes that are connected more distantly. While such systems exist for finding and reaching relevant structured and unstructured and semi-structured data, they're insufficient for finding relevant confounding variables from unstructured data sources, such as satellite imaging. Causality-focused data processing and mining, and novel indexing methods, which incorporate non-traditional relevance criteria, can provide a path forward in this area. This robustness research challenge also requires us to consider how to address data quality issues in a more careful manner when we expect to conduct causal inference on the results. So our second issue is that tables with missing rows and values in this particular example may introduce selection bias, also sometimes referred to as Bergson's paradox. Such biases crop up when the pattern of missing or repaired data alters the observable distribution of the population. So let's say implicit in our data set, the curator decided to add weather details to the database only when the extreme weather events occurred. Later, we find this table with the missing rows and we apply standard issue data imputation techniques to patch up the table. The issue is that such methods change the probability distribution of this attribute, as well as the mutual information it shares with all the other attributes, which we also can use as a guide to find potential confounders. This change in distribution, of course, also opens up opportunity for selection bias. As we can see, since the actual values for these cells are for clear or rainy weather, by using data imputation techniques, we could have just assumed that all of them are snow or thunderstorm related, for example. So one common approach is to use inverse probability weighting, which is reweighting complete tuples to preserve the shape of the attribute's distribution across values. However, assigning weights to these tuples when the values are extracted might not be possible because the underlying probability distribution might be unrecoverable. Under such circumstances, sometimes the best we can do is just to estimate and determine a promising reweighting and to do it well in a performant manner. Beyond this, there's also other data quality issues like functional dependencies, complex table relations, outliers, and others, which can also welcome a host of possible biases and skews that confuse causal conclusions. All right, third, having an incorrect causal DAG can result in incorrect query answers through confounding bias. So let's return to our running example. For the sake of this example, we're only going to look at this trio here. The edges on this graph perhaps make sense. Given any particular city's airport, the available airlines that fly there aren't the same. Departure city also impacts departure delay since the size and geographic realities of a city might result in delays regardless of other factors. But what if this arrow is missing from our causal DAG? We'd mistakenly believe that we don't have to adjust for departure city in our calculation and end up having a spurious correlation. So part of the reason why this challenge is actually called conciseness is that these correctness issues get exacerbated once a graph becomes more complex. While there exists structured learning and causal discovery methods in machine learning and stats to learn these graphs, the learned graphs end up being hairballs for how dense they turn out in practice. And of course, finding erroneous edges in a hairball just gets harder. What's critical is to ensure that these graphs are still human scale accessible, since the complexity grows exponentially with respect to the size, and our capacity to verify these graphs would be quickly overwhelmed if we didn't shrink them somehow. So we could try and summarize a source table and then create a graph, or we could build a big graph and use some graph summarization technique like dedensify. It remains to be seen whether you can still use these graphs for causal inference, and how you would be able to determine whether one summarization is better for another for a causal domain. There's also plenty of other questions to explore in this realm, but let's quickly pop back up to causal data integration as a whole. In the last few minutes of this talk, I'm going to show you the inner workings of the CDI system and a taste of the prototype. So recall, our vision of causal data integration is to build systems that mine and assemble data and background knowledge for answering causal questions. So with this in mind, we can sketch out what that system would look like. We start up with a user and a table they want to run causal queries on. By the end, the system should output a single and complete relational database and a correct causal DAG for use in causal inference. And in that process, the CDI system should address the 3 challenges that we just discussed. The first step is to build a knowledge extractor. This module identifies causally relevant attributes to include for analysis from provided data sources, which can include data lakes, knowledge graphs, and unstructured data like images and videos. Next, using the base table and the causally relevant attributes from the extractor, the data organizer module constructs the augmented data table by overcoming data quality issues like missing rows and functional dependencies, complex table relations. With this high-dimensional data table, the summary causal DAG builder constructs a comprehensible and compact causal DAG that ensures the causal inference task can be answered. This module also might elicit semantic knowledge from external sources to aid in the creation of this graph. So now that the user has what they need, they can proceed with answering their causal question. Zooming back out, here we have our CDI system. We extract attributes from available data sources, we assemble the augmented data table, and we build a summarized causal graph for use in a causal inference. As a proof of concept, we implemented a prototype which we call Cater. Let's see it in action. Let's imagine we're a user who wants to answer, how does the identity of a country impact COVID mortality rates? Let's see what we can do without CDI. We go online when we find a table with COVID case counts. This table has 15 attributes, and 2 of them represent the causal question we're asking. Since we don't have a causal graph and the table is small, we use an off-the-shelf causal discovery algorithm to find a graph that fits the characteristics of the data. To answer our causal question, we need to find mediators in the graph and adjust for them to find the direct effect. We get a significant direct effect size, and this is actually not right. Based on intuition, the COVID mortality rates should be based on characteristics of the countries, whether it's densely packed, whether its citizens have high mobility, whether it's very hot or humid, rather than just the country itself. So it would do us right to be able to adjust for some of these characteristics. But the thing is, the data set we have doesn't have any of these attributes. It just has a country and its COVID numbers like case count and hospitalization rates. So at this point, we can just choose to quit and hope the internet has what we need, or we can start manually cleaning, preparing, and augmenting the data table we have with whatever sources seem reasonable. So let's look at what happens when we replay this scenario with our CDI prototype Cater. We start with the same base table with a country mortality causal query marked. From our knowledge extractor, we find 436 attributes from DBpedia, which are then whittled down to just 15 additional columns in the table with the data organizer. Our DAG builder constructs a summarized causal graph. Instead of having 30 nodes, this simpler graph just has 11. In addition to the base table info like country and COVID spread, we see that dashed line nodes contain information about the economy, climate, ethnic groups, and geography. So again, we find the mediators in the graph, determine direct effect, and we get no direct effect. Our big win here is that the user didn't need to spend time and effort to conceptualize, find, and integrate all these other characteristics into their analysis. The causal graph is compact and understandable so that we can also inspect and verify the claims on that causal graph. So to recap, we introduced causal data integration, a new line of research to mine and organize information for causal inference. Unlike conventional data integration, we curate a complete data table robustly augmented with all causally relevant attributes from provided data sources and an interpretable, concise causal DAG. We built a prototype with promising preliminary results, and we can't wait for you to join in on this work. Thank you for your time, and I'm ready to take questions.